So with inverses, this first problem right here, we're going to do what the directions say. We're going to graph the original. All right, so we're going to graph these points. Remember, on the first number that you graph, you put the dot. This first one moves left or right, and the second one moves up or down. And then we're going to connect those dots. So these three, I mean, there's only way you can draw this is going to be a triangle. But when you get into where you have more than 3 points, make sure that you connect them in connect them in order. So this one you can't go wrong. All right, so here's the first one. Now this, with the inverse, what we do is, and if you look at your notes, the inverse, the first thing you want to do is you're going to switch x and y. So if you want to write an inverse function, everywhere you see an x, which this is an x, 3 is x, and you're going to put a y in that spot, and then everywhere you see a y, your second number here is y, you're going to put an x. So basically, if you're given a point, you're just switching those. And then the next one was -7, 4. It will become 4, -7 on the inverse. Now, so that you don't get confused and think that this is all supposed to be the same thing, you might want to put a note out here to remind yourself that these points represent the inverse function. Now, the reason that you see this line down the middle here, that is your y equals x line. That line right there is y equals x. That's the equation for the line, because if you look at every point, all of your x coordinates are the same as your y. Your x's equal your y's. So for instance, the point 1, 1, your x coordinate equals the y, 2, 2, 3, 3, 4, 4, and so on. You get way up here, the point 10, 10, you're going through that point because your y and your x are equal to each other. All right, now what is interesting about this, an inverse function, what it does is it takes every point, every segment on a shape, every curve on a shape, and it reflects it over this y equals x line. So this point right here, if you reflect it over the y equals x line, you're going to go straight toward it, and then your point will end up over here. If you go straight toward it at a 90-degree angle, okay, your point will end up over here. So the distance from this point to that line, hold on, it's going to try to disconnect. So the distance from this point to that line, it will have the same distance to your other point, or to your inverse point. So let's plot those points and see where we are. So the point 83 would be here. Now notice, if we go straight toward the line at a 90-degree angle, we measure that distance right there, it's going to be the same as this distance. So this point is a reflection of this point over the y equals x line. And that will happen every time. So when we get to this point over here, we reflect it over the y equals x line. It's going to be down, somewhere down here. And this point will get reflected somewhere over there. So we do the 4, -7. You see how that point is the reflection of this point? And the -5, 6, that point is the reflection of this point. And then we connect those. So this triangle I'm drawing now, that is your inverse triangle. That is your inverse function of the original. So that's what you're doing on these problems. All right, so I said to find the inverse of a function, you're going to switch your x's and y's. Okay, so that's the first step. When you're looking at this problem here at the beginning, it doesn't have a y. All right, notice it has an h of x. Here's the x, that's great. The h of x is actually your y. So since there isn't a y that we see, if you have a function notation right there, you switch it to y. So now if we want to find the inverse, put a note, because when we're going to find the inverse, we're going to switch the x and y. So wherever you see a y, you're going to put an x, and wherever you see an x, you're going to put a y. So it becomes this. So I put this little note out here, inverse, so that you wouldn't look at this, and then if all you had written down was that next, wonder how did you get from there to there, and you would assume that those two are the same, and they're not. So this is a function, and this is a completely different function that actually this function, if you reflected the original over that y equals x line that we saw before, you would get this function. All right, so the next step that we do after we switch those is then we solve for y. So when you solve for y on this one, you're going to get y by itself, so you're going to subtract 5 from both sides. That leaves you x minus 5 equals y. So now y is by itself. Now we usually write the y on the left side, so then I'm going to switch those around here. All right, since it's an equal sign, doesn't matter which side the things are on. And the last step that you want to do is you want to actually write it in inverse notation. Which means you're going to have a little -1. Okay, I'll put that as a reminder. So to do that, instead of y, just like originally we had an h of x and we changed to y, now we need to change back to the h of x. But let me go ahead and write that down first. All right, but you'll notice that originally h of x was x plus 5. Now we've got that it's x minus 5. So these two right here, they can't be the same notation because they actually equal two different things. So to show that it's an inverse, we put a little -1 right here. This -1 does not mean it's not an exponent. That's just a little notation that means it's the inverse. All right, so don't get that confused, because h of x, that's not even a variable, that's a name of the function. This is function h, it has an x in it, and this means, oh, that's actually the inverse of function h. We're going to do the same thing here. So we are going to first rewrite it so that there's a y instead of a k of x. So this is function k, and it has an x in it. You look over here, yep, there's an x. That's the letter that we're going to see. So now we're going to find the inverse of this function. And to do that, wherever you see a y, you're going to put an x. And wherever you see an x, you're going to put a y. If there had been another x back here, you would have put a y right there. Second step, get y by itself. So we're going to add 3 to both sides. And then to get rid of the square, we're going to square root. And if you square root the right, you have to square root the left. But whenever you take an even root, when you're solving an equation and you take the even root of the other side, so if you're like if you were trying to get rid of a fourth power and you came over here and did a, okay, let me go back for a second. So if you had some stuff here and you had the fourth power If you came in to get rid of that 4, you would do the fourth root. If you do that on the other side, you'd have to put a positive negative there because it's an even root. If it was an odd root, you don't have to do that. So if this was a third power, to get rid of the third power, you take the third root. You would not have to do the positive negative. So continuing, I'll need the positive negative over here because I took an even root on both sides, you have to put the positive negative right there. So continuing, we're going to have a positive negative square root of x plus 3. The square root canceled out the square, and we're left with y. Instead of a y, we're going to write it as, we want to use that k of x notation, but since this is an inverse, we put a little negative 1 there. And it is equal to this. So that is your inverse function. Now, you could, so if you're supposed to determine whether each pair of functions are inverses, you actually have two options. If you wanted to, you could come up here and find its inverse. And then if it was that, then you know, yes, they're inverses. Okay, so that's one option. Another option, going back to things that we've learned recently, would be to work out h of g. Okay, that is where you take the function g and you plug it into h. If that is equal to x, then it might be a function. But then you have to go and check to make sure that if you switch those around, g of h also has to equal x. All right, so if your first attempt, h of g, if you try it out and you get x, then you have to also make sure that g of h equals x. If h of g did not equal x, it equals something else, then you know that no, they're not functions. So we're going to try this method. All right, so I'm going to take h of g. So remember, you take the function g and you plug it into h. So h is 3x, so it's 3 times stuff that we're going to put, like this is where the x is. So we're going to take whatever g is and we're going to plug it in there. This is your function g. So function g is going to get plugged in to function h. All right, so when you work that out, 3 over 1 times 1 over 3 ends up being 3 over 3, which is 1, times x, which is x. So when you're looking up here, h of g, so far, so good. So now we need to find g of h. So this time, we're going to start with function g, and what we're going to plug into it is h. So you're going to take function h, which is 3x, and you're going to plug it in to g of x. So g of x looks like this. All right, so I put parentheses where you see the x for g. And now we're going to take the h and plug it in for g. So we're going to take this h and we're going to plug it in. So this 3x gets plugged in where the x was. When you work this out, since 3 over 1 is the same as 3, if you multiply across the top, across the bottom, 3 over 3 is 1. We've got their x in there. So they both end up being equal to x. So that's a yes.